My name is Yong Kwon from Purdue. This is a joint work between Purdue, University of Georgia, and Wisconsin Madison and SRI International. So let's first talk about the cyber attacks. Cyber attacks these days are becoming more and more sophisticated. In particular, advanced persistent threat, or APT, is a special kind of attack that leverages most advanced attack techniques. APT targets specific organizations such as government agencies. In recent years, we have seen many high-profile APT attacks. For example, Stuxnet targets the most dangerous infrastructure, which is nuclear plant, endangering the entire human being. The retail giant Target paid $18 million for their data breach that affect 40 million of their customers. And Office of Personnel Management of United States hit by APT attacks again, affecting 18 million of employees. And the well-known Democratic National Committee email hack in 2016 was also believed to be done by an APT group. A typical APT attack starts from learning the target organization to prepare targeted attack, and they either leverage social engineering, such as phishing emails, or vulnerabilities, such as zero-day exploit, to enter the victim organization. And once they enter, they move slow and stay low. They lurk in the systems for a long time, understanding what's going on in the organization and infecting other systems. And at the end, they either exfiltrate on important data or disrupt the systems. So let me first present an example APT attack to explain how the APT attack look like in the wild. This APT attack is generated by professionals, and the goal of this attack is to exfiltrate on important data. So the attack starts from a classic phishing email. When an employee opens the phishing email, it says he needs to extend his car insurance. When he clicks the link, it opens a Firefox web browser showing a login page. When he tries to log in, it downloads a PDF file saying that it contains an important notice. Then when he opens the PDF file, his computer is compromised because this PDF file is indeed a weaponized PDF file that contains malicious payload. Because this PDF file contains a known zero-day exploit, security tools installed on his computer, such as antivirus software, fail to detect this attack. And once the attacker enters the organization, he stays low and moves very slowly. So it takes weeks to compromise other systems, understanding what's going on in the organization, and locating an important document. And finally, he located the secret document, but it was encrypted. So he finds a program called GPG to decrypt the secret file. And once he gets the decrypted secret file, he moves file to a home folder of an FTP program. Later, the attacker connects the FTP server to exfiltrate important data. So after a month, the company realized the secret is stolen. Then they hire a forensic analyst to investigate this case. The forensic analyst first collects the system call logs for past 2 months and identify a suspicious symptom, which is file exfiltration through the FTP process. So now let me show how the forensic analyst ideally trace back the attack using a causal graph, which is commonly used in attack investigation. So causal graph consists of system subjects such as processes and system objects such as files and network addresses. In this example, I use oval to represent subject and diamond to represent object. And arrows between system subject and object essentially indicate the direction of the information flow. So the forensic analyst first identify how the secret is obtained through the GPG process, and also understand how the malware compromised system and download it from the Firefox. And he later also understand the Firefox web browser is downloaded from the email client and also from the phishing email. This is an ideal causal graph that contains all and only attack-relevant system subject and object. And before my work, there were 2 existing attack investigation techniques called audit logging and taint analysis. Unfortunately, using these 2 existing analysis tools to get this ideal causal graph is not easy. This is because they have difficulty accurately identifying dependencies between system subject and object. So now let me introduce why the existing technique have difficulty accurately identifying dependencies. So the first type of attack investigation technique is audit logging. It essentially records system code such as socket read and file write and detect dependencies between them. They essentially focus on the dependencies that can be directly inferred from the production audit log. But the problem is they rely on coarse-grained assumptions. For example, audit logging-based systems assumes that system codes operate on the same files are all related, and also within the same process, output system codes are dependent on all preceding input system codes. And such coarse dependency causes false dependencies. For example, in our attack, before the victim received the phishing email, he also received many benign emails. Again, before he navigated the malicious website, he also navigated many other benign websites. Unfortunately, such benign emails and a web browser website becomes bogus dependencies in the causal graph. For example, even in this small attack, a forensic analyst ends up with a causal graph consisting of 55 processes, 41 files, and more than 400 network addresses, while only a small number of them are actually attack relevant. And such false dependence cause a problem called dependency explosion. And in practice, this dependency explosion problem delays the investigation from days to weeks, sometimes even months. The second attack investigation technique is taint analysis. It's essentially track dependencies by monitoring data propagation of individual operations, such as assignment. In this small 2 lines of code, input is assigned to X and Y is computed from X. And we can see Y is data dependent on X. Unfortunately, taint analysis technique suffers from significant overhead because they need to monitor every instruction. And more importantly, taint analysis technique have difficulty handling control dependencies. In our case, because of the control dependency, taint analysis failed to track important dependency between secret document and GPG process. And this resulted in losing the entire attack chain. So to solve this problem in 2016, I proposed an accurate and precise causal analysis technique called LDX, or lightweight dual execution. It follows the original concept of counterfactual causality, first introduced by David Hume in the 18th century. So the definition goes like this. Okay. Given 2 events, such as system codes, a later event is causally dependent on a preceding event if changes at the preceding event leads to state differences in the later events. So essentially, I implement a system that follows the same idea. I run 2 executions and make sure these 2 executions are exactly same except the perturbation that I make on the input system code. Then when output system code, I compare 2 executions to infer causality between perturbed input system code and output system codes. So the LDX is significantly faster and more accurate than state-of-art taint analysis technique. It only has 6% runtime overhead and 3 times more accurate than the state-of-art taint analysis technique. But unfortunately, it requires instrumentation of the target programs. So when we try to apply this LDX in enterprise environment where the actual APT attackers target, we encounter the instrumentation requirement is problematic. In fact, in enterprise environment, changes on end-user systems is not allowed. For example, modifications to the commercial programs are not allowed, and organizations such as companies, they have usually internal policies that do not allow modified kernels or programs to be used. So instrumentation-free is a key requirement in the enterprise environment. So let me first introduce key intuition behind my instrumentation-free causality inference technique, which is behavioral decomposition. It means a complex system-wide behavior can be decomposed into several primitive operations. So let me give you an example. Here I have a small story that a user opens a secret files and copy and paste the secret contents to a new file, and he edits the new file. And later he encrypts the file and sends it outside. This story can be decomposed into 5 primitive operations. For example, open, copy and paste, edit, and encrypt, and send it out. And more importantly, the same set of primitive operation can be used to describe more complex combinational system-wide behavior. For example, here I have another story that has more actions. He edits more files and send it out more files too. Again, this story can be described by the same set of operation, same set of primitive operations. So now let me introduce my model-based causality inference. So first, I use LDX in offline to acquire causal models for primitive operation. Specifically, given a program, I run the program with the input that can exercise primitive operation on LDX to infer causality and build a causal model. This is a graphical representation of the causal model. Each node represents system calls, and edges on top represent dependencies. In each node, we have system call name, and its subscript represent the file handles of the system call. And in production run, I use this causal model to parse production audit log. Specifically, given a production audit log that does not have any dependency information and causal model that has dependency information, I only use subsequence of the system call in the causal model to parse the production audit log. This is because production audit log does not have any dependency information. Once I identify the instances of the causal model, I derive dependencies from the causal model to the production audit log. And we encounter two prominent challenges. First, language complexity. This means the sequence of system call in the causal model could be very complex so that it requires expressive language to describe. For example, here I have a program has two for loops with the same iteration count. This program can generate a sequence of system code that requires context-free language to express. Here is another example, has a for loop, and the first and third for loop has the same number of iterations, and second and fourth for loop has the same number of iterations. And this can generate sequence of system code that requires context-sensitive grammar to describe. But unfortunately, more expressive language lead to higher cost in parsing. Another prominent challenge is ambiguity problem. This means some of the system code in the production log can be parsed into multiple causal model instances. Let me give you an example. Here I have a causal model consists of two system code on a different files. When I use this causal model to parse this production audit log, I may have multiple causal model instances. For example, R1 and W2, W3, W4, and so on. Because different causality can be derived from different model instances, this could cause incorrect causality. And then I realized the root cause of this problem is that I treat the production audit log as a plain sequence of system calls without any dependency information. And we have important observation that certain dependencies can be extracted by preprocessing audit logs to reduce language complexity and ambiguity problem. For example, here we have two system calls operate on the same file, which we call explicit dependency. So the basic idea of my technique is leveraging this explicit dependency to help parsing to reduce language complexity and ambiguity. But we also know, in addition to the explicit dependencies, there are other dependencies, which is implicit dependency. These implicit dependencies are caused by memory operation during the execution. That means we cannot extract these implicit dependencies by processing the log. So we use LDX to derive these implicit dependencies. The basic idea of my algorithm is to leverage these explicit dependencies to derive implicit dependencies from the causal model to the production log. So let me give you an example. Given an explicit dependency from a causal model, I first identify the corresponding explicit dependency in a production audit log. Once I identify the instance, I use it as a boundary to search the remaining subsequence of the system call in the causal model. So in this example, we take the the middle two system calls and scan within the boundary. And once I identify the instance within the boundary, then I derive the implicit dependencies from the causal model to the production log. So now you can see the parsing only happens within a small segment of the production audit log, and it only uses small segment of the causal model. We call this algorithm segmented parsing, and it significantly reduced language complexity and ambiguity problem. So we evaluate our MCI on a week-long system-wide experiment, including large-size programs such as Firefox, P2P programs, and web servers. And it precisely identifies all the causality with less than 1% false positive and false negative. We also tested on 3 months of Purdue web server and 2 months of NASA web server workloads. It includes 9 million requests and 4.2 unique requests. It only has 2.5 false positive and less than 1% false negative. And we also test on various APT attacks constructed by professionals. This is one of the graphs that is generated by the state-of-art logging, audit logging-based technique. It contains 18 files, 33 network addresses, and 8 processes. And this one is even simplified graph. And this graph is the one generated by our tool. It only has 3 files, 4 network addresses, 8 processes. And as you can see, this is concise and precise causal graph that includes all and only attack-relevant system subject and object. So in conclusion, I present MCI, which directly work on production audit log without any changes on end-user systems. And it is scalable to handle large-scale, week-long experiment, including Firefox. And we infer causality very precisely with less than 2.5 false positive and less than 1% false negative. And most importantly, my name is Yong-Ik Won from Purdue University, and my research focuses on solving system security problems using program analysis. And most importantly, I'm on the job market. Thank you very much.
If you're hired, you can form a line right over there.
Sure. Yan Chen from Northwestern. Great work. Just a clarification question. I think in your slide, you show that as a training phase, you use LCX. Mm-hmm. So does that mean you still need to instrument all the applications before you can, do the MCI work?
Mm-hmm. Excuse me, couldn't hear the question clearly.
Oh, okay. Let me repeat it. So in your presentation, mm-hmm. Seems there are 2 phases, right? Offline training and then online kind of use the MCI, right?
Right.
Then in the offline training, mm-hmm. It seems you still use LCX, LDX. I'm sorry, LDX, mm-hmm. which still require all the instrumentation of the applications.
Correct.
Is that right?
Yes. So the offline analysis will be done in the lab environment, so it requires instrumentation. But in production run, we don't need to have any instrumentation. We can just collect the log from Linux kernel
uh-huh.
audit log, which is already implemented, and you just need to turn on the flag. And then we can use our model parser to infer the causality without any changes on the end-user systems.
I see. For the LDX, I can work instrumentation directly on binary, right? So you don't need the source code.
We actually work on LLVM bit code, which is a little bit different from source code. Yes.
Okay, then yes. If you don't have the source code, can you still use your system to?
Yeah, I think because LDX actually cares only about the control flow, I believe we can actually port it on the binary. So yes.
Okay, thank you.
Mm-hmm. So I think I have a related question. Mm-hmm. The causal models are the thing that sort of need the offline analysis, right? So they're primitive operations as opposed to having to profile every single application, and that's sort of one of the big gains in terms of deployment. Is that correct? Okay. Uh-huh. So I was just wondering, in practice, how easy is it to develop a complete set of causal models for a system? And although you sort of like in this end-to-end evaluation, you said the false positives are quite small. Are there any particular causal models where there's a lot of confusion and that can cause fits?
Usually, these false positive and false negative, we find that there are similar primitive operations that, for example, there is like save and save as. Then when we only have the save, then we probably miss some of the causality on the as part. But we also find that these missing causalities are not that important in the attack investigation. And also for the training part, most big programs, they provide these test cases, so we leverage these test cases to get the primitive operations.
Great. Another question?
So I'm kind of wondering how vulnerable you are to the classic mimicry attack. For example, your example is like, I see a read of a file, that's file 1. I'll look for another write to a file 1, and whatever is in between, I'll assume there's an implicit flow between them. If I want to hide the real implicit flow, wouldn't I try to read file 1, put some garbage in between, write to file 1 before I do the really malicious things? Or you think down the road your parsing will self-correct?
So let me actually clarify the question. So are you asking about the accuracy of our causal analysis? Is that correct?
I'm asking if somebody is explicitly trying to screw with you by modifying their system call sequence, how bad are things going to be? Can I move your boundary around so that you will assume the wrong implicit flow is happened and miss the right implicit flow?
So let me first clear the. I think there is a confusion between that you are saying that you are an attacker and your program can some sort of like have different sequence of the system called order. Actually, what we are focusing on here is we are trying to identify causality through the benign application, because when the APT attack happens, that's how they propagate, and that's what matters in the APT attack investigation. So in a benign application, attacker cannot, add or remove or change the order of the system calls.
What if I control hijack your file?
We might need to take this one offline,
Yeah.
but let's thank our speaker one more time.